I like those discussions. Carry on. Hi, class. How are you? Better than this morning. You know, some mornings you're like, I'm feeling peppy now, so just in time for you guys. How are you feeling, Rachel?
Oh, I'm good.
Let's see. Luke, Rachel. I'm learning some of yours. Mel. Did you go by Vicky or Victoria? Victoria. I looked yours up and I can't remember. Drew. I saw your picture, so you're looking familiar. I don't know if you know. When do they take your pictures, actually? I've always been curious as a student, because as under class administration, I have an option to view a class roster by picture. And I was curious, when you become a student, do they take you and take your picture? Or? I wonder if they're just using the same picture.
Probably, because that's the only time they've ever taken my picture.
Okay. Well,
Also, like,
they,
prefer pictures from behind, like, stop blinking.
of course, granted, some of you look a lot different. Especially if you're a senior by now. And you're starting. You have to choose to upload it? Well, that would explain why some of you don't have a picture showing. Oh, and that reminds me. The lady behind, you had a question the other day. Oh, I never got an email from you checking about your click. Oh, okay. And is Jiling Liu here? There he is. Do you have your laptop with you? Oh, okay. You know how you logged into Canvas and checked your settings? And we checked your display name and your official name. There's a third option there down called sortable name. Will you check that one also? So there's three places at the top and then display name. And there's something called sortable name. Tell me what yours says. That's what their suggestion was. We already took care of everything, but we want to... Okay. All right. Well, let's see. We've had a few equations to guide our thinking, so I wanted to write those down first. Let's see. We've had velocity. Well, I don't need to do that. How do we find velocity? Velocity. It's a philosophy about velocity. Okay. Anyway. Distance over time. So I'm going to emphasize a change in position over time. But yeah, distance over time. If you prefer, doesn't bother me. So velocity is a rate of change of position, distance over time. All right, what was acceleration? Very good. Change in velocity over time. And this one, it is specific. It's not change in speed. It's change in velocity. Difference being there's direction. If the direction changes, you're accelerating. Good. Oh, we rearranged this. Change in velocity can be found if you know the acceleration in time. And then I talked about if you knew how fast you were going initially, you would just add this to that, right? Because this is how much your velocity changes. So you could rewrite this as final velocity minus initial velocity. And then move the initial to the other side. Because some of you might go on in physics, and this is how they just start with this. But do you see how this is just the change in? You end up at something, you started at something. And if I move that over, it's just like, how fast are you going at the end? Well, how fast were you going initially, plus that change. So you start out at some speed, velocity, and you change it by that much, so you end up at this velocity. But I know some students are more mathematically inclined, so there you go. Oh yeah, then there was at the end of last time. How your position changes with acceleration. So this being distance, or if you prefer, a change in position. Same idea. If you accelerate for a certain amount of time. So specifically with free fall or gravity, where this acceleration is due to gravity, 9.8 meters per second squared. We discussed that. After 1 second, you've fallen. It works out to be 5 meters. But then what was it, 20, and then it increases. There's beautiful pictures in your book. I think that was, oh yeah, we also had your weight, which is a force, was mass times gravity. That has come up. That should make more sense by the end of today, because that's actually comes from Newton's second law, which is what we're getting into today. Any question about those at this point? Oakley dokley. So, we know what acceleration is now. And I bet you even know what produces it. What produces an acceleration? A force. Very good. If you want to change something's motion, you got to apply a force. That's how I write this. Acceleration is proportional to, directly related to the net force. And I emphasize net because we've had a lot of that discussion. It matters of all the forces acting on it. Just one force tries to make it accelerate one way, but if there's a second force, it could try to accelerate it the opposite way. So the net force determines, technically, the net acceleration, if you will. So they're directly related. Chapter 4 discusses friction and then emphasizes the difference between mass and weight. And doing so, then it builds to the second law. So that's what we're going to do. Friction. It's already come up. You've already told me it's a force. But you should know there's two types of friction. Static friction, when something isn't moving, it's not in motion. Or once it's moving, sliding friction. So there's two types. We'll call it static friction and sliding friction. They're both forces, but they're not always the same. For those of you that go on, sliding friction is also called kinetic friction, because kinetic means in motion. And generally, static friction is greater than or equal to the sliding friction. Let me show you, hopefully. Or at least give you an idea of what we're talking about. So, this is sandpaper on sandpaper. And I'm going to make it heavier. So, this is a scale. It shows force. So, if I pull on the block, you can see that I'm pulling with now 10 newtons of force. So, I'm pulling on the block, it's pulling back on the scale. There's tension in this rope. This is measuring that tension and showing how much force I'm trying to pull. Well, if I'm pulling the block, let's look at the motion of the block. It feels a force of 10 newtons that way. Why is it not moving? Because it feels a greater force this way, or at least is equal. It must be 10 newtons this way. We actually know it's exactly equal. Because if this was bigger than this, it would start moving that way. If this is bigger than this, it would move to your left. So they must be balanced. So if I'm pulling with 10 newtons of force, friction is pulling back that way with 10 newtons of force. And before it starts moving, that's what we call static friction. So let's see how much it takes to get it moving. If I go slowly, 9, 10, there we go. Now once I keep going, it's not a big difference. But what I hope you can see is that it takes a little bit more to get it moving. Then once I'm moving, it drops a little. So let's try it again. Could you see it that time? So the frictional force initially was larger to break some of those bonds between the two surfaces, or to physically break some things. It's that microscopic thing that's happening between them. But once you're moving, it's generally easier to keep moving at a constant speed. And so there the forces would be balanced also. Or at least I tried to be in this instance. So before it moves, we're in mechanical equilibrium. Yes? While I was moving, if I move this at a constant speed, what's the acceleration? 0. So what's the net force? 0. Does that make sense? And if that's 0, then the force I'm pulling, that the scale is showing, is the sliding friction. They're balanced. And in that case, it was less. That's all there is to friction. Your book also emphasizes that speed doesn't matter. Whether you go fast or slow, it's the same amount of friction because they're the same surfaces. Or friction this way versus this way. The friction's the same because it's the same materials. The area doesn't matter. That'll affect other things like pressure and heat, but the actual force is the same. Friction's actually pretty messy and complicated, but that's all we need to know for most everything we deal with. So speed doesn't matter. Surface area doesn't matter. Just whether it's moving or not might affect it. We use a symbol mu. It's a Greek letter mu for static friction. And can't use an S. It's probably why people use K for kinetic friction, if you want to use a symbol. Friction's pretty straightforward. Do you have any questions? All right, let's re-emphasize the difference between mass and weight. I like this one. If you go to the moon, does your mass change?
No.
Does your weight change?
Yes.
Good. Your weight does change, but your mass wouldn't. So here's a massive ball, and I can hold it. Gravity's pulling down, so there's a weight down and a supporting force up. It's tension in the string, and they're balanced because we're in equilibrium. So I can do a couple things. I can lift it up by applying an upward force and raising it. But I can also go quickly, like this. You ready? Are you watching? We call that a jerk. No, the ball, not me. That's my, standard joke. So when the string is on there, what's the difference? Why does it break in one case but not another? Here it doesn't break. I can move it up and down. But if I jerk it, it broke. Why? I am exceeding the string's tension. So that's telling us what about the force there? Yeah, there must be more force. Why is there more force? I mean, does this change its weight? Am I changing its mass? So what's going on? Yeah, my acceleration. I'm trying to change its motion more quickly. Remember the tablecloth out from underneath the plates? The heavy things do what? They want to stay in place more. This has a lot of inertia. And mass is a measure of inertia. So this has the same mass whether I do it slowly or fast. But if I try to do it fast, it's going to resist me more. And so that's when it breaks. You can't really weigh things out in space. You can't put it on a scale, right? Because if you're out away from where there's gravity, it doesn't act down. You can't support it. But you can still tell that something's how much mass it has. Instead of doing this, how heavy is it? Well, nothing's pulling it down out in space, right? So what could you do to get an idea of how big it is? Because this won't work.
Try to
Did you guys hear that? She's right. Good job. Push it horizontally, like this. This would be the same. The resistance I'm feeling back and forth to move it would be the same out in space because this has so much inertia, so much mass. So I hope this is helping to clarify the difference between mass and weight. Mass is just a property of the matter and how much it wants to resist change anywhere. So if you're on the moon, you might be able to lift up a heavy car, right? Because there's less gravity there. It's being accelerated down less. So maybe you can lift it up. But if you try to push it, it's going to be the same as if you were here on Earth. It's still going to be hard to move because it has lots of mass and inertia. So that tells us, through experimentation, that the acceleration, we'll call it net, is also proportional to the mass. In this case, if the force is bigger, there's more change in motion, acceleration. If that's bigger, that's bigger. In this case, where do we put the mass? If there's more mass, do we have as much acceleration? Or do we have less? We have less. So you put it on the bottom. We say this is directly proportional because as one increases, the other increases. This is inversely proportional because if you make m bigger, that makes this fraction smaller. It's going to resist you more with more mass, so there'll be less change in motion. Does that make sense? So Newton just put these together. Okay, we know acceleration is now proportional to F on the top, mass on the bottom. We observe that. It's proportional to those two things in that ratio. And so with almost every formula in physics, it starts like this. Now, how could we figure out if it was exactly equal? Well, you do some experiments and find out. And in this case, it's exactly equal. That's Newton's second law. There's no constant of proportionality in this. They're directly equal. You have probably heard that formula before, some of you, whether you realize it or not. F equals ma. Who's heard of that before this class? F equals ma. That's Newton's second law. That's how you sum it up. Written this way helps me remember more of the relationships. That you increase the force, it'll cause it to accelerate. And you know what that means now, change its motion, velocity. But if it's more massive, it'll have less change. So it's just acceleration is proportional to those two things. Straightforward. Now do you see that this is the same as this? That's just a specific force. The weight is mass times acceleration. In that case, due to gravity. This is generic. This works for any force. It's its mass times acceleration. So you can think of acceleration as two different ways now. This and this. You can look at it in terms of velocity and time or force and mass. All right, let's do some more forces. I like this one. I need some volunteers for this. Who would like to help me play Tug of War? Because I can't do it. Come on down. If you want to play, come on down. We can have two sides. This is a phone book. During a movie, I interweave the pages. They're not glued together. They're not taped. Okay, I did put tape on the outside just so this thing doesn't unravel, but I think you could pull apart Scotch tape. This isn't going to work with one person. Come on. You grab that end. The way this works, as they're coming down, is it's like taking a deck of cards and trying to shuffle. And they're just interwoven. I did this one every other one. So it's like taking the pages and just doing this. So go ahead. You grab that side, and pull away. Rip it apart. A little harder. Who wants to come help them? Okay. Come on, we can do it. Good job. Thanks. I've actually hung from this. Who likes Mythbusters? Do you see that episode? Were they able to do it? What'd they get up to? Were they actual tanks? I can't remember. They were really big trucks, I remember. So. Yeah, and again, this is just frictional force. There's a lot of area. People think, oh, it's because there's more area. That's actually not what's going on. I think it actually ripped apart, but it didn't rip where the pages were connected on Mythbusters. It ripped here where it was being clamped. It just tore in half. But where they were connected. So when you do this, there's two ways you can pull it apart. If I grab the two ends like this, you can very easily pull it apart. That's because I have superhuman strength. Maybe some of you can get ideas for your superhero paper. But if you grab the ends this way and squeeze them together and then try to pull them apart, it's a lot harder. And some of you might think I'm faking, but you can go home and try it. Why is it harder that way? The frictional force must be larger, and it is. Who knows what this is?
Oh, Chinese finger charm.
Yeah, you want to do it? How do those work? Chinese finger trap, we call them. What do they call them in China? No, there's no such thing? Must be like fortune cookies. It's an American thing. So as she tries to pull apart, the way those work is they clamp down on her. They're increasing the support force, just like if you squeeze the deck of cards.
They really don't have these in
They're being pushed together harder. It's like they're heavier. There's a bigger support force. And so that increases the friction. And so with the phone book, when you try to pull it apart, it's trying to squeeze together. And the harder you pull, the harder they squeeze. And that creates a supporting force. Thanks. So you don't have these at all? That's funny. Americans. So maybe this anyway, at least a lot of Americans know what these are. So you can see that it gets skinnier in the middle. So as I try to pull them apart, it scrunches together and increases the supporting force. They're now pushed down harder. Because it is true, the heavier something is, the support force has to be stronger, and that will increase the friction. So I thought that was fun. Let's drop some things. Falling objects. Oh, we'll play guns first. These are toys, but I've always wanted to figure out how to use dart guns in lectures, so I finally did. What you do is you compress a spring, and that stores energy. We'll discuss that more later. But they're pretty much identical guns, identical springs. They're going to exert equal forces on the two darts. This dart's more massive. So if I shoot them, we'll shoot them up. What the heck? What'll happen? One will keep going and one will drop? So the other one won't drop?
No, it will eventually.
Eventually. So one will hit the ceiling and the other won't? So one will go higher than the other. Okay, which one will go higher?
The lighter object.
Why will the lighter object?
Because it has more acceleration.
But they're feeling the same force.
But it has less mass.
Yeah.
Has less mass, which means what?
Which means that needs to have greater acceleration if they have the same net force placed upon them.
Very good. Very good. You look at Newton's second law down here, circle F equals ma. If, let me draw it, because I like this representation. I'll do it now. If they're both feeling the same force, and you have a little mass and a big mass, well, this one must feel a big acceleration and this one a little. Do you see that? Or in terms of inertia, the one with more inertia will feel less of a change for the same given force. So I concur with you guys. Let's do the experiment and find out. See, we have our educated guess, our hypothesis. Now we do the experiment. Drum roll, please. You called it, Rachel. That one, it did hit the ceiling. The one without the clay. And the one with the clay didn't go as high. All right, this one, at the top of its motion, what was its speed? All right, so what was its acceleration? Thank you, good job. I heard a couple people. 9.8 meters per second squared. Gravity, it's still being accelerated down. Good job.
In that case, would gravity be negative? A negative force?
If you define up as positive, then negative is down, and gravity's always down. So the acceleration was down while this was going up. When it stopped at the top, and as it came back down, the acceleration was always negative. All right, now we can drop things. Let's do this with free fall. Free fall is basically when you're they define it as you're dropping things and the only force acting on you is gravity. So if you drop a book, after 1 second, how fast will it be going? 9.8 meters per second. Yeah, because it accelerates at 9.8 meters per second every second. So yeah, after 1 second, it'll be going 9.8. How far will it have fallen in that first second? That's the squared one. 4.9 what? Meters, yeah. 4.9 meters using 9.8. The other day we used 10 meters per second squared, and it would have fallen 5 meters. We were rounding. Yeah. Do you raise your hand if you don't see that, please? Or I'm just using the 1/2 AT squared. Oh, hey. Okay, this is fun. See, you can now use this as a tool. If you ever have a well, or you want to know how high up something is, or how high up you are above something, or how deep something is. See, I think the last time I used this was on the San Francisco Golden Gate Bridge. My sister-in-law spit her gum off the ledge, which is illegal. But the geek came out in me, and I asked her to do it again. And she was happy to, so she got another piece of gum, spit it off, and we timed how long it took. And honestly, I don't remember now. But let's say it took 4 seconds. So she 1001, 1002, 1003, 1000, oh, splat. How high up were we? That's all you need to know. You guys have enough information now. How high up were we if it took 4 seconds to hit the ground? Let's see, shall we? Do we know the gum's acceleration? Yeah, 9.8, because it's in free fall. So that's G. To make our math up here easy, let's just do... And what was the time? Okay, so 1/2 of 10 is 5, and 4 squared is 16. 16 times 5 is 80. So yeah, boom. Using our physics knowledge, I knew I was 80 meters up. I knew how high above the ground we were, where she spit her gum. Cool, huh? All right, for you Americans. Oh, yes?
How much does the bolts are actually spitting it out have an effect on it? How much is folding?
Good question. See, you're thinking like a scientist. That means she didn't just go and let it fall straight. Yeah, she gave it a good hawking, Wachoo! And it went like that. And this is the point of chapter 10, when we get to projectile motion. But hey, I don't mind skipping ahead. Vertically, what's the acceleration for both cases? It's the same. Horizontally, is there an acceleration? Initially for this one, to propel it. But once it's out of her mouth, Nothing propels it this way. But acceleration horizontally would affect how far it goes this way. Do you think it takes long? Which one would hit the ground first? If they were both released at the same time, one that dropped straight and one you shot out. It's a tough question. It shouldn't be that easy. That's what we're going to do. The biggest demo we have, actually it's that one, does this. I'll let you think about that. It's a teaser. It's in your book. But the clue is they both fall the same distance vertically. And so it's the vertical acceleration that affects that and how long it would take to go vertically. So I think some of you already have the answer, but I'm going to let you think about that. So, in America, some people do. Raise your hand if you honestly have no idea how far 80 meters is. Oh, only a couple of you. Okay, you guys are good. Then I'll just leave it as a meter is roughly 3 feet. So it's about 240 feet. Gives you an idea. You had a question.
Yeah, so what if you're standing on the bridge and throw something like straight down the horses?
Okay, if you throw it down, then initially it's going to have, when it leaves your hand, an initial velocity. Instead of just 0, it doesn't fall from rest. It starts out at a certain speed. Would that hit the ground faster? If I threw this one down at the same time I just let go of this one, which one would hit first? What's your gut tell you?
I think it would depend on how high you were.
On how high you were?
Yeah, because then, if you were higher, then there would be more forces pushing that on it, like air or...
Oh, okay. So if you start taking air resistance into account, which we're going to, things change. Yeah. Without air resistance, which one would hit the ground first?
Probably about the same.
He thinks the same. Who agrees? Without air resistance, you throw one straight down, and you just let go of the other. Who thinks they'll hit the ground at about the same time? We got 2 votes. And who thinks the one you drop will hit the ground first? Who thinks the one you throw will hit the ground first? Oh, that's the majority today. The majority is correct. And it's just because who hits the ground first is who gets there in the least amount of time, correct? So let's go back to this guy. This one. If you just drop it, this is 0, correct? In the vertical direction. Vertical. If you throw it, this is something. So the one you throw is going faster the whole time than the one that drops. So it'll get there first without air resistance. Does that help? Yes, in the back? Without air resistance? Is there a point they would fall where eventually they'd end up the same speed? Without air resistance? No. With air resistance? Probably. Let's do that, because you guys are there. I keep saying I'm going to drop stuff, but I haven't yet. Huh? So, all right, gravity check. Who's going to hit the ground first? Sure? And you guys know why. What are the forces acting on the book when they're falling? Gravity, it's weight down. And air resistance up. Yeah. These are roughly the same shape and size. Air resistance has to do with the surface area. So for that, they have about the same air resistance. But who has more mass? The book. So he has more inertia. He's affected by the air resistance less. So he falls faster. And the paper has a smaller net force, right? So you have weight down and air resistance up. If they're balanced, what's the paper's speed? Speed. If the two are balanced, its weight and air resistance increases to its weight, so they're equal. We're in mechanical equilibrium. What's the net force? Well, so what's the net acceleration? So what's the velocity? Constant. It's not changing. That's what we call terminal velocity. And every object will reach that eventually. Even us jumping out of an airplane. Your terminal velocity. At some point you won't start going any faster. You're still too fast. And if you open a parachute, your terminal velocity will be less. But if you're at terminal velocity, that's when you're in mechanical equilibrium and you're not increasing your speed or decreasing. Your net acceleration is 0. You're no longer picking up speed. So this paper easily hits terminal velocity. You can kind of see. Well, yeah. Then it starts tipping and changing its surface area. But yeah, right about there. It's already reached its terminal velocity. But the book doesn't. It just keeps picking up speed. If we dropped it from a big enough height, eventually it would hit a terminal velocity. Would this guy's terminal velocity be more or less than this guy's terminal velocity? Yeah, if we dropped them both high enough, once they got to their respective terminal velocities, whose would be larger? Or would they? Okay, we got to vote for equal. When do you reach terminal velocity? What are the conditions? You stop accelerating. Good. What forces are balanced?
Air resistance and gravity.
Gravity and air resistance. Okay. Whose weight's bigger? The book. So we got big weight down, which requires a big air resistance up. And it's going to take longer for this to reach that much air resistance. This one will have fallen further, longer, before you get a big enough force up to balance the force down. That's when terminal velocity kicks in. It doesn't increase anymore. So by the time that happens, it will be going faster. It will have fallen further. So it had more time to accelerate. You with me? So that means this guy's terminal velocity will be bigger once it gets to terminal velocity, because it has more time to accelerate. This one reaches it really fast, and so it hasn't picked up much speed. Now we're at terminal velocity, and it just stays at that speed. Questions about that? Yes?
Is terminal velocity 0, or is it?
Terminal velocity is not 0. If it was 0, you wouldn't be moving. But you're still falling. It's just it's staying constant. Terminal in that you've reached a value that you're not going to go past. It doesn't increase anymore because you're no longer accelerating, trying to change that. There's no net force from Newton's second law to try to change your motion. So, if a large person and a skinny person both jump out of an airplane, open their parachutes, and fall, will they hit the ground at the same time? No. Who will hit first? The heavier person. Because their terminal velocity will be reached a little later, so it'll be greater than the lighter one. So they'll reach the ground first. So yeah, if you go with your girlfriend or boyfriend or spouse and you jump out, whee, and you let go, well, if you weigh a lot more than she does, you're going to hit the ground first. Everything else the same.
What affects air resistance?
What?
I mean, other than
What affects air resistance? The shape of the object, which is pretty much the surface area that's hitting the incoming air, and speed.
So, air resistance in different parts of the world or in outer space.
Oh, that too, yeah. The density of the air matters too, the fluid. So the more dense fluid you're in, the greater the air resistance. For example, this falling in air versus in water. Or trying to move your hand through air versus in water. There's more resistance. We call that drag. Air resistance also called drag. So yeah, what you're in, the shape of the object, and how fast you're moving. The faster you move, the more resistance there is too. That's, I hope, intuitive to you. Take your hand and move it in fluid. Go slowly, you don't feel much resistance. Go fast, whoosh, and it feels like it's pushing on you more. That's the concept there. All right, let's get rid of air resistance. do you think? Because they both accelerate at the same rate, right? So if you can eliminate or minimize air resistance, they're both accelerated down at the same rate. But my question to you is, which one feels a greater force? Or do they? I mean, they both hit the ground at the same time. So how do the forces compare? Yeah, that's what people think, that the forces are the same because they hit the ground at the same rate. Yeah. Which is why I bring this up. As soon as I remember where I put the chalk. So, in this case, the force was the same. Between the book and the crumpled paper, what's the same? That we know for sure is the same. I heard it. Yeah, the acceleration is g, right? If there's no air resistance, they both accelerate at the same rate. Gravity is trying to change their motion equally. However, if the book has a big weight, because it has more mass, the paper has less mass, so it requires less force. It weighs less, but the ratio is the same. This ratio and this ratio. That's Newton's second law. If you want to accelerate something at 9.8 meters per second squared, and it has a lot of mass like the book, then it requires more force to accelerate it. That's why a book is heavier. If it's a crumpled piece of paper, there's not as much mass. It doesn't resist change as much, so it doesn't require as much force to achieve the same acceleration. And this is a big confusion for people that don't take physics classes. They know that most people will agree that things fall at the same rate. They'll hit the ground at the same time. But it's not because the forces are the same. They can be drastically different. It's because the acceleration is the same. Do you guys know who likes amusement park rides? Why do you like them? Have you ever thought about why people enjoy amusement park rides? What, Rachel? The thrill. What thrills you? Adrenaline. What gets your adrenaline flowing? Blood. Good, Rachel. Yes. No, she's right. It is a kind of vague, open-ended question. Yeah, have you ever thought of what? Possibility of death. That's right. That's true. Yeah, most people like it because you're in motion. It's that you're moving. Almost every ride is doing something. But it's not how fast you're going that gives a thrill. Everybody been on an airplane? I mean, you're cruising. But sometimes you forget you're on an airplane, right? It's not how fast you're going. What is important? The acceleration. When they build roller coasters, they don't care how fast you're going. At the bottom. They want that change. How quickly can they change your velocity and have a larger acceleration? And they do that with speed, but also direction, right? That's what thrills us and gets our blood pumping. Rachel's right. So yeah, if you went on a ride with no acceleration, well, go back to the airplane. You're cruising along at, 300 kilometers an hour. Well, whoop-de-doo, until you hit turbulence, right? Whoa, and it's trying to change your direction. Then everybody's like, whoa. That's what people do or don't like. Yeah? Is there acceleration when there's no speed? And your gut is?
Yes.
Can you give me an example?
I think there was a question like that in the homework, and I didn't really understand. But it doesn't seem like there would be, because you always need speed to change direction.
Can you have an acceleration without speed? So your speed is 0,
Yes.
but you're accelerating?
Yeah.
Okay, I can think of an example that we've discussed, actually, it's the same example, but we've discussed it a couple times in class even. So yes, it can happen. Can you think what it was? throwing the ball up in the air. This. At the top, what's its speed? Now. 0. But is it still accelerating? Yeah, so there's still a net force on it trying to change its velocity. But for that brief moment, its velocity is 0 because it's changing directions from positive to negative. I'm glad you brought it up. Here's another one because we'll just use this guy. You don't have to crumple the paper up. You ready? What do you think will happen now? It's just because the book is blocking the air from hitting the paper. So in all instances, there was no air resistance. So they've accelerated at the same rate. Um, 3 minutes. I was going to I had some clicker questions prepared. I'll start with them next time because by the time we get into it, you guys will just... So let's end with this guy. Relative velocities, and last thing I'll do. If this has a velocity, it's constant because it doesn't seem to be going any faster. But we say its velocity is relative to the table. It's moving relative to the table. You can move this board, though, too, and change relative velocity. So if the car is going, I don't know, looks like it might go a meter every couple of... Oh, the heck with it. A meter a second. We'll just keep it easy. And you move the board. This is tumble. Bueno. So, if this is going 1 meter per second to your right, and the board moves at 2 meters per second to the right, what's the velocity of the truck relative to the table? 3. Good. What if the truck's moving 1 meter per second to your right, and the platform is moving 5 meters per second to your left? What's the velocity of the truck relative to the table? -4, or 4 to the left. Yeah. That's really all I wanted to emphasize, because your book discusses that, and there's some questions. That's like you're in a car or in a truck. If you're in a truck going 85 miles an hour, and you throw a ball out the back end of the truck, whoosh, relative to somebody standing on the ground, the ball does not seem to be going as fast as you think it was. You know, because if you throw it at 60 miles an hour, whoosh, you just created, darn chalk. What did I say? If you had, let's say, 80 this way, and you throw it 60 this way, you only think, somebody standing on the ground thinks it's only going 20 miles an hour. But you could throw it the other way. So next time you're in your car, that's your homework for the next several days. Pay attention when you move things. Toss something up in the air. It's got inertia, right? If you're traveling with your car, so is the chalk, right? You're going 85 miles an hour. So if you toss it up, does the chalk stop going horizontally? What's its speed relative to the ground? Or next time you're on a plane or a train, think of some of these things. You can have fun with your neighbors. Any last minute questions? Okay, I'll see you guys next time.